Hi, I'm Paul Turnbull, and this is Munro Live. Welcome. We're with Munro Associates, an engineering consulting firm, and we do lots of teardowns of motors, vehicles, and we like to highlight great examples of amazing engineering, and this is one of those things. We've been asked a lot of questions from our previous videos about the difference between induction motors and permanent magnet motors. They're both electric motors, but they have different strengths and weaknesses. And so we find that they work very well together in electric vehicles. So I'm going to go through and talk about the physical differences of the two kinds of motors, a little bit about how they work, and we're going to discuss those strengths and weaknesses, advantages and disadvantages of the two different kinds of motors. And then we'll look at the performance differences and come to the conclusion that it's a good idea to have both kinds of motors in the car so that we can take advantage of the strengths of each. So that's the plan, and it's a lot to it, so let's dive in.
This video is brought to you by Anker and their new MagGo wireless charging station. The MagGo wireless charging station is the ultimate companion for your Apple ecosystem, allowing you to charge your iPhone, AirPods, and Apple Watch all at the same time. All of the modules are MagSafe compatible for a hassle-free wireless charging experience. And when you're not charging, they can be folded up for easy storage. The compact size of the MagGo wireless charging station is true to our values of lean design, but it doesn't compromise on capability. Thanks to its 15-watt ultra-fast charging, you get a lot of power in not a lot of time. Its size also makes it the perfect travel companion, so you can stay charged no matter where in the world you are. Best of all, the MagGo wireless charging station is designed to keep your devices safe, equipped with advanced temperature control, overvoltage protection, and many more unique safety features. You don't have to worry about heat or damage while you charge. Use the link and discount code in the description to get your own MagGo wireless charging station from Anker today.
First of all, let me talk about the physical differences between these two motors. In the case of the permanent magnet motor, the rotor has permanent magnets. In this case, this is an interior permanent magnet motor where the permanent magnets are down inside the rotor. You can't see them from the surface. And there's lots of different ways to put these permanent magnets in the rotor. This is a different rotor where you see this kind of a V shape, and that's a whole other topic for another video. Let me know in the comments if you'd want to dive into why they arrange the magnets in the permanent magnet motors. This type of motor is called an interior permanent magnet synchronous machine. We're going to talk a little bit about that later. Induction motors, again, these are both electric motors, and they both use the same kind of a stator, where it doesn't matter how you wind the stator, you can use stranded wound or bar wound. So both permanent magnet motors and induction motors use the same kind of stator. But the difference is the rotor, and induction motors don't have any magnets. So instead, the rotor is made up of a whole stack of laminations like this. And then typically, we take molten aluminum and pour it down the slots, the gaps in the lamination. And that forms these bars called rotor bars. And then at the other end, all the bars are shorted together with a ring to form a circuit. And in some cases, when I remove all the steel, you get something that looks like this. And we've been calling this in the motor industry the squirrel cage. And so induction motors are sometimes called squirrel cage motors. So you have a bunch of bars, of conductors that are shorted at both ends by big rings of either copper or aluminum, any conductor that's convenient. The aluminum is usually a little bit cheaper And if you want higher efficiency, you can go to copper. These are both used today in production in electric vehicles. So that's the physical differences between permanent magnet motors and induction motors. But we need to talk a little bit about how they work. So both of these are examples of AC motors, but in reality, all motors are AC motors. Even the so-called brush DC motors that people may be familiar with, the brushes and commutator turn the DC from the battery into alternating current inside the motor. In this case, we use something called an inverter to turn the DC current that comes from the battery into AC current that the motor needs to work. So we use a computer-controlled inverter, which is a set of 6 switches, and how inverters work is amazing. Maybe another topic for a video. Let me know in the comments if you'd like to hear more about how inverters work. But we use the inverter to turn the DC into AC. We feed the AC current, or 3-phase AC current, into the windings of the motor. So when you put electricity into windings, these are coils of copper wire surrounded by steel, you get an electromagnet. So we turn this thing into an electromagnet with this AC current. But the special thing about it, and the great gift to humanity that Nikola Tesla gave us, is that by putting AC current into a stator like this, you get a moving magnetic field. It's a little bit like at a stadium where the crowd does the cheer, like the wave. So each individual person is just standing up and sitting down in their seat at the right time, but everyone can see the wave of the cheer going around the stadium. So the wave moves even though the people don't. And we do the same trick in the stator of this. We just turn on and off the electricity in one place, but by doing that, we can create a wave of magnetic field that travels round and round the stator. So when we do that with the stator and we put a permanent magnet rotor into the stator, then the magnets want to try to follow the magnetic field around. So if I am an observer sitting on the rotor, so if I was like a person sitting on a merry-go-round, and I was looking at that wave in the crowd in the stands, as I'm going around, I would always see just people standing up as I go around. It's as if the wave was standing still from my perspective as a person on a merry-go-round. So from the perspective of the rotor, this moving wave going around the stator is stationary compared to the rotor. It's in sync. So as the rotor spins, the wave of the magnetic field of the stator is synchronized with the position of the magnets. And it's in a position such that the magnets of the rotor are always between the magnets of the stator. So this is a north pole. It always wants to pull towards the south pole of the stator, and always being pushed by the north pole, which is here. So we always have both a push and a pull that's pulling the stator rotor around with that magnetic field. So as the magnetic field rotates around, it pulls and pushes the magnetic fields of the permanent magnets in the rotor. So that's how permanent magnet motors develop torque, by using this moving wave of magnetic field from the stator. Induction motors, on the other hand, have no magnets. And so what we do exactly the same trick with the stator. We make a rotating magnetic field, but we make the magnetic field rotate just a little bit faster than the rotor in the induction motor. And so the field is moving as compared to the rotor. As the magnetic field moves, you have this changing magnetic field, which generates a voltage. And when that changing magnetic field, that's Faraday's law, is changing magnetic field creates a voltage. And that voltage drives a current in the bars of the rotor. And the current just goes round and round in a circle, an eddy current, round and round. So as the magnetic field passes by, it generates current inside these rotor bars, and the current flows around in a circle. As soon as you have current flowing around in a circle with steel around it, you get an electromagnet. So we use the moving magnetic field from the stator to induce a magnetic field in the rotor. And the magnetic field in the rotor and the magnetic field in the stator interact in exactly the same way as it did on the permanent magnet motor. So once we have a induced magnetic field in the rotor, then this motor ends up operating just the same way as the permanent magnet motor. So that's the 5-minute physics explanation for how motors make torque with electricity. So let's talk about the advantages and disadvantages of these two different ways of making torque with electricity: induction motors and permanent magnet motors. So we got it listed here: induction motors on the left and permanent magnet motors on the right. From the advantages perspective, in engineering and certainly Munro Associates, we help people save money on all kinds of manufacturing products. If you're doing that with electric motors, one thing you need to look at is cost on the rotor. And these permanent magnets that we put in the permanent magnet motors are expensive. And the molten aluminum that we use, or even the copper, are both less expensive than the permanent magnets for the permanent magnet motor. So the induction motors have the advantage of lower cost. It's not as big an advantage as one might think, because in order to make the same torque from an induction motor, you need to make it a little bigger. Because the permanent magnet motors produce more torque for the same package size. And so you're making it a little bigger. That means you're paying a little more for the copper and steel in the stator and rotor in order to get the same effect. But after all is said and done, the induction motor has a cost advantage. And that's beneficial, but it's not the primary reason. It's not the make or break for why one might choose an induction motor. The second thing, this lower spin loss, is the key advantage that induction motors have. And I need to talk a little bit about what spin loss is. So when you turn the motor off, and the motor is just spinning along, so you're just gliding in the car. So the car is moving, but you've taken your foot off the accelerator. There's still some loss because it has bearings, and the bearings they're almost frictionless, but not perfectly frictionless. And you're spinning and you're stirring up the air inside the motor, and that produces a little bit of loss. But induction motors, the spin loss, which is the loss when the motor is off, is very low. Permanent magnet motors, on the other hand, have this as a disadvantage. Because of the permanent magnets, when it's spinning, even if you have the electricity off on the stator, the permanent magnets are creating this moving magnetic field which wants to induce electricity the same way we induce it purposefully in the induction motor. The permanent magnet motor is inducing current in the steel of the stator. it wants to induce it producing a voltage, and it wants to produce electricity in the windings, but we open up the switches on the windings when it's turned off, and so no current can flow. But even so, the little bit of eddy current losses that you end up generating with a permanent magnet motor leads to higher spin loss. So there's this issue with permanent magnet. You can't turn off a permanent magnet. And so because of that, it suffers this extra spin loss when the motor is turned off. Fortunately, in electric cars, the motor isn't turned off very often, except when you want to brake, come to a stop, and in which case you kind of want the extra drag. So permanent magnet motors, this is not a huge deal, except for certain situations in the car where this causes us trouble. The permanent magnet motor, by contrast, it has higher torque density, and higher efficiency than the induction motor in general. And this leads to a smaller package, lighter weight, and generally the higher efficiency is the key here, because every watt that you save with the motor is a watt that the battery didn't have to deliver. And so if you want to go 300 miles in your electric vehicle, you want to do that with the smallest battery possible. And if you can do it efficiently, you don't need as big a battery to go the miles. So higher efficiency is a real premium for for electric vehicle applications. And so that's why the permanent magnet motor, this alone, is why permanent magnet motors, especially this interior permanent magnet synchronous machine, is usually the choice to go with. So those are the advantages and disadvantages of the permanent magnet and induction motor. I put up here the synchronous versus asynchronous. The way we make torque, as we call it, is with these we put the electricity into the stator to make this traveling wave, and we'd make that traveling wave move in sync with the permanent magnets in a permanent magnet motor. But in order to produce power with the induction motor, we have to make sure that the traveling wave of electricity and magnetism in the stator is always out of sync, a little bit faster than the rotor. So we call this an asynchronous motor. So those are the advantages and disadvantages, and a little bit about how they work. So let's look at some examples of performance, the performance differences between these two kinds of motors, which will, I think, drive home the point of why it's a good idea in many cases to have both of these kinds of motors in the car to take advantage of the strengths and weaknesses of each. We take advantage of the strengths of each and ignore the weaknesses. So for the induction motor, what I've plotted here is torque here and speed of the motor. So torque, and this is called a torque speed curve. And so at 0 RPM, each of these motors can produce large torque. And then as the RPM increases, these motors can hold what's called a constant torque out to some speed. Usually the RPM here is roughly 35 to, translates to 35 to 45 miles an hour. So you have this constant torque, which gives you a great feel off the line. So you get this constant acceleration for the car, right at the limit of what the tires are able to deliver. So this constant torque is an ideal feel off the line up to some point, and at some point we reach the limit of what the motor is able to do. This would be the maximum power coming out of the motor. And then the torque drops off along what's called a constant power line. So as the speed goes up, the torque drops off, but we're delivering the same peak power. And then with induction motors, something happens at about, this would be near highway speed, or 60 miles an hour or so. That magnetic field from the rotor starts to work against you. It starts to fight back against the current of the stator. So as you're putting the current into the stator, the impedance of the circuit, the AC circuit, increases with frequency. We want to get as much torque for every amp that we put in as possible. So that's great when you're down here at low speed. But that same high inductance that generates the large magnetic field for every amp that we get, later that large changing magnetic field starts to work against us. And we can no longer put in the current that we'd like to put in, and the torque drops off. So induction motors have this issue of not being able to produce high power at high speed. Permanent magnet motors, on the other hand, do the same trick with a constant torque up to 35 or 45 miles an hour. And then they produce nearly constant power up to essentially infinite speed. The speed limit here is only determined by the speed at which the rotor holds together. So we try to make the rotor mechanically robust so it can spin really fast. And that allows us to use a large gear ratio to give us great torque at the wheels. So it can hold that really high constant power out to extremely high speeds. So that's one of the advantages of permanent magnet motor over the induction motor. They also have a little bit different regions of high efficiency. One thing I wanted to point out with efficiency is that the definition of efficiency is power out over power in. And since the power out is zero along this line, so if you're putting in zero, if you got zero torque, you're getting zero power out. And it's also zero along this line. If you're not spinning, then you get zero power out. You can produce torque, but no power. And so the efficiency is zero along this line, and it's zero along this line, but it reaches some maximum efficiency out at moderate torques and moderate speeds. The induction motor is efficient out to high speed, but not so efficient at low speed, because at low speed, I have to put energy in order to get the magnetic field. And so that energy that I'm putting in to get the magnetic field, I don't ever recover. And so at low speeds where the powers are low, the efficiency is low for induction motors. Permanent magnet motors, on the other hand, since we get the magnetic field for free, we pay a lot of money for the magnets, but in terms of energy, we don't put energy in to get get the magnetic field. So at very low speed, the permanent magnet motor reaches a very high efficiency. So it's really great for city driving. The asterisk here I've put is the point where a typical city driving operating point. So when you're driving in the city, you have this torque that's in this neighborhood and speed like this. So it's like 35 miles an hour and 1/3 pedal position for your torque. Typical city driving. This other asterisk is highway driving, typical highway driving. So this is 70 miles an hour. You're on a flat level road. You're only fighting against wind resistance and rolling resistance of the tires. And so the torque needed to keep the car going 70 miles an hour is small. You don't need to be flooring it to keep the car going. So it's relatively low torque. So if you're delivering the torque, so one option, if you have both these motors in your car, one option would be to split the difference and have half of the torque delivered from the induction motor and half the torque delivered from the permanent magnet motor. But that means that each torque is cut in half, and you're down near the, both of these are down near the x-axis, which is where efficiency is low. And so it's much better on the highway if you're flat and level and you're not passing anyone, to turn one motor off and deliver all the torque with one motor, and so that it's much closer to the highest efficiency operating point. Now you might think, oh, let's turn the permanent magnet motor off because the induction motor is very efficient at high speed. And that would be great, except that the permanent magnet motor, when you turn it off, you can't turn off the permanent magnets. And so the permanent magnets are still spinning. They're still generating this back EMF, this voltage in the stator, which is inducing currents in the steel of the stator, and therefore creating a drag torque. And so the permanent magnet motor produces this drag torque, and so the net effect, your efficient induction motor has to carry the permanent magnet motor and its extra drag torque. It actually works out better to turn the induction motor off and use the permanent magnet motor. And this one, the induction motor, is not producing any very low spin loss, only the bearings and the air. And this one is operating near its most efficient point, but not right on it. But still, the net losses with this off and this running is optimal. It's the best way to go. And so what we have here is, by knowing that the companies are putting induction motors and permanent magnet motors in their cars, we know that they're running this live efficiency optimization algorithm. And so every instant, as you're driving down the road, listening to tunes, kicking back, there's a computer that's deciding what is the best way to deliver what the customer wants right now. And it's selecting which motor to use. Sometimes it is the induction motor, sometimes it's the permanent magnet motor, sometimes it's a combination of both. It selects the best motor to use live every hundredth of a second. And so that's why, and when we see this kind of brilliant engineering as we tear apart vehicles and analyze what the industry is doing, we at Munro just love to see that. And I think the engineers deserve a lot of credit for coming up with this type of thing, and we wanted to highlight this. And I personally, on behalf of a driver here as an EV driver, I just want to say thank you to all those engineers that came up with brilliant stuff like this. And it just is very exciting to me to get a chance to see it in action. Thanks a lot.